Okay, so now we are looking at vector differential calculus. So I'm going to be doing these questions. There are 4 of them. So basically they cover the gradients of a scalar function. They cover the divergency theorem. They cover, we're also looking at Cauchy-Riemann theorem, and then we are going to do the last question. I think it's the line integral. So we're just going to be doing these questions, and I'm trying to dive deep in those concepts, but I'm going to also do a separate video about explaining each and every concept in detail. So okay, let's just go straight to this first question. So this is question 5a. So this is one of the past exam papers for engineering maths 301. So you're saying if x is equals to x cubed plus y cubed plus z cubed minus 3 xyz, then they're saying find the gradients. So this is there. We know that this is the vector operator, the vector differential operator. This is the vector differential operator, right? So, and we know that the gradients, how do you define the gradients? So if this is your function, if this is a scalar function, scalar point function, let me just pick a scalar point because it's defined on a space, on a regional space. So this is a scalar point function that is continuous. This is very important. It's continuous and differentiable. If this is a scalar function that is continuous and differentiable in a regional space, then the gradients of the function, the gradients is defined by del phi is equals to del phi del x I plus del phi del y j plus del phi del z k. So that's basically it. And what you have to understand about the scalar, we are evaluating a scalar point function. When you're looking at the gradient, we're evaluating a scalar point function, and once we've evaluated the scalar point function using the del operator, we expect to get a vector quantity, which means del phi is a vector quantity. That's why here we have the unit vectors. So okay, let's just do this question. So what do we do? So in here we have f of x, here we have phi. So that means del f is going to be what? Is going to be del x of f del x of f, which is, this is f minus, this is minus 3yc I plus, we're just using the del operator, and then x cubed plus y cubed plus z cubed minus 3xyz, this is j plus del z of f again minus 3yz, this is k. So what you do actually, you need to remember this for the gradients. So this is, we're using the del operator, so we're just going to differentiate the function itself with respect to x, y, and z. And then so here, differentiating this with respect to x, which means y and z are constant. So del f is equals to, so if we differentiate that, what do you get? So differentiating, we're saying x is a constant, or y, z are constant. So we're going to get 3x squared, y is a constant, minus 3yz, this is I, plus differentiating this with respect to y, what do you get? It means x now and z are constant, so that will give you 3y squared minus 3, differentiate that with respect to y, it's xzj plus, and then differentiate this with respect to z, which means x and y are constant, so this is minus 3. With respect to z, this is going to be xy. Okay, so now we have differentiated each, we've differentiated the function. We've differentiated the function that we're given with respect to x, y, and z. And when you look at the question, they said at a point 1, 2, 3, right? You look at this, they're saying at the point 1, 2, 3, which means you're evaluating the gradients at a point. So how do you evaluate the gradients at a point? So we're evaluating this gradient at a point 1, 2, 3. So where there's x, y, and z, we're just going to substitute those coordinates, and we're going to find the vector. So from here we can just say, because this is x, y, z, this is going to be 3. What is x? X is 1. 3. What is y? Y is 2. What is z? Is 3. This is I, plus 3. What is y? Y is 2 minus 3. I'm substituting here now. And then x is what? X is 1 here. Since x is 1 here, y is 2, z is 3. Then z is times 3. This is j. This is j plus 3z squared is going to be 3 squared minus 3. X is 1, y is 2. This is k. So which means your gradient at the point 1, 2, 3 is going to be what? So this is basically 3 times 3 is what? It's 9, and then 9 times is 18. 18 minus 2, this is minus 15i, plus, and then this is going to be 4 times 3 is 12 minus 9. This is going to be 3j plus, and then evaluating this is 9 times 3. It's 9 times 3. So that is okay. So 9 times 3 squared. So 3 squared minus 3 times 2. So this is basically 21. Okay, so this is the gradient for this function. So as you can see, this is a vector quantity. This is a vector quantity. So now this is a vector quantity. So now let's look at they are saying, this look at B, they're saying show that the vector this is irrotational and find its scalar function. So what do you mean when a vector is irrotational? So now I will introduce another concept whereby we are talking about the curl of a vector. The curl of a vector. Before I reach there, so let me just talk about the solenoid vector. What is a solenoid vector? A solenoid vector, we are saying a vector F is said to be a solenoid. Is said to be a solenoid, or is said to be solenoidal if the div of that vector is equals to 0, or divergence of that vector is equals to 0. So be cautious about the divergence of a vector. If the divergence of that vector is equals to 0, we are saying that vector is a solenoid. So hopefully we'll find the equation here. Okay, but an irrotational vector, we are talking about a curl of a function. Okay, let me just explain the divergence of a function. So divergence of a function before I move on to question B. A divergence of a function, divergence of a function. So basically, if again you have your function x, y, z, it's continuous. This function is continuous, differentiable. It's continuous, differentiable in a given region. We are saying the div of that function, and I'm using a dot product here. This dot means it's a dot product. The div of that function, you represent as div f or the del operator dot, which is a dot product. This is basically equals to this will equal to del f, or this will equals to del phi 1 del x plus del phi 2 del y plus del phi 3 del z. So this is how you evaluate a divergence. So what you have to understand here is that with the divergence, we are looking at a vector point function, and after evaluating a vector point function, we are going to get a scalar point function, which means f is a scalar point function. You get a scalar point function. Unlike with the gradient, we evaluated a scalar point function to get a vector point function. With divergence, you evaluate a vector point function to get a scalar point function. But this is what you have to remember for divergence. Okay, so and now I want to introduce the concept that you're going to use to solve question B to show that this is irrotational, that function is irrotational. So we need to look at the curl of a function. A curl of a function, again, we are going to say if phi x, y, z is differentiable, is a differentiable vector, it's a differentiable vector point function, differentiable vector function at each point that I'm going to say it's x, y, z in some region of space, then the curl of that function, or we represent it using the cross product, is going to be I j k del x del y del z, phi 1, phi 2, phi 3, where obviously x, y, z is equals to phi 1, right? Is equals to phi 1 I plus phi 2 j plus phi 3 k. So this is a curl of a function. So it's supposed to be differentiable at each point in some region. So this is how you evaluate it. So let's come back to this question. Show that the vector this is irrotational. What do you mean when a vector is irrotational? Let me explain an irrotational vector. Irrotational vector. An irrotational vector. An irrotational vector. So we are saying a vector is said to be irrotational if the curl of that vector or is equals to 0. If the curl of that vector is equals to 0, then you say that vector is an irrotational vector. So these concepts are very important because they use them for application, as you can see in this question. So now our task is to show that this vector is a curl. This vector is irrotational, and find its scalar potential. So I'm going to show you how to find the scalar potential of a vector. But okay, for now, let's start with the first task. So we are given that this is B. Looking at the vector, we are given that f of z or f of f is equals to 2x z squared. F is equals to is equals to 2xz squared plus y squared plus 2x y minus z. This is I, this is j, and then plus what is k? K is 2x squared z. 2x squared z. This is 2x squared z minus y plus 2x. This is k, right? So now let's find the curl of this function. So how do you go about doing this one? This is simple. Here you just need to pay attention. Sorry, this is simple. So now we just go straight to the curl. So this is the same thing as f1, f2, f3, right? So the curl of f is equals to I j k. So del x del y del z. Then f1 is what? Is 2xz squared plus y squared. Then f2 is 2xy minus z. And then here we are going to have 2x squared z minus y plus 2x. So this is how you evaluate the curl. So from here, obviously you apply the same concept when you're finding the determinant of a 3 by 3, or when you're evaluating the modulus of a matrix. So this is going to be, remember, we close. If you close those two, we are going to have this times this minus this times this. So when you're evaluating this, let me just use square bracket. We're going to have del y of 2x squared z minus y plus 2x minus del z of 2 of this one of 2xy minus z, right? And this is my I. And again, a cal has to give you a vector function. A cal has to give you a vector function. This is a vector point, has to give you a vector point function. This is very important. And then minus, remember this is plus, minus, plus, right? So this is minus, and then if we're evaluating that, so which means we're going to cross this part, and then this times this times this. So hopefully you still remember that. So this is minus, so we are going to have del x of 2x squared z minus y plus 2x minus del z of minus del z of 2x z squared plus y squared, and then plus, and then which means we close this. Now we're going to multiply this. We're going to multiply those, and we have del x of 2xy minus z minus del z of del y, not z, del y of 2x z squared plus y squared, and then this is k. So let's evaluate this. So let's differentiate. So let's differentiate this with respect to y. If we differentiate that with respect to y, we are expecting z and x are constant. Differentiate that with respect to y, so we are going to have a minus 1 here, and then minus this minus is this minus. So differentiate this with respect to z, it's going to be minus 1 again here. It's minus 1. This is I minus, this is the minus here, and then now we're differentiating this with respect to x, which means z and y are constant. Differentiate that with respect to x, we are going to get 4xz we are going to get 4xz, right, minus 4 minus so let me double check. With respect to x, and then this is going to be, I'm sorry, let me just confirm this. This is z not x, yes. So I'm sorry, I think I made a mistake when I was writing this is z not x. Yes, that is z not x. This is z not x. Okay, so if we're differentiating that, we're going to get 4x, right, z. So that with respect to x, differentiating this and minus, differentiating this with respect to z, we are going to get 4xz again, and then this is what? This is j. So this is j plus, for k, differentiate this with respect to x is going to be what? It's going to be 2y. Differentiate this with respect to y, it's going to be minus, which is this minus, differentiate this is going to be 2y, also this is k. So therefore you can see that del is equals to negative 1 plus 1 is 0i. 4xz minus 4xz is what? This is the minus, this is 0j, plus 2y minus 2y, this is 0k, therefore this is 0. This proves that this vector f is irrotational. This vector is irrotational. That's the proof. So that's how you solve this question. That's how you solve this question. And then now just look at how to find the scalar potential. So finding the scalar potential is actually easy. So for the scalar potential, you need to remember something. A scalar potential F is equals to, this is the formula that you're going to use. So already we know f. What is f? So here we know that f is 2x z squared plus y squared I plus 2yx minus z j plus 2x squared z minus y plus 2z, right, k. We're saying this is equals to del phi. Remember we said del phi is what? Is del x phi I plus del y phi 2. This is 1 j plus del z phi 3 k. So which means you're equating the f of x to that del x phi 1 j, oh sorry, I plus del y phi 2 j plus del z phi 3 k. So now I, j, k are the unit vectors. So we're going to equate the coefficients of those unit vectors from both sides, which means del x phi 1 is equals to 2xz squared plus y squared, and then again del y 2 is equals to 2yx minus z, and then del z phi 2 or phi 3 is going to be 2x squared z minus y plus 2z, right? So now you just need to find phi 1, 2, 3. So which means you're going to integrate both sides. So integrating both sides, integrating del x phi 1 with respect to x, because there's x here. So you do that on the other side, 2xz squared plus y squared dx, and what do you get? This is phi 1. Integrating this with respect to x, what do you get? You get x squared z squared plus y squared x plus c1, and then you do the same thing here. We're going to integrate del x phi 2 or del y, sorry, dy is equals to 2yx minus z dy. So from here, this is phi 2 is equals to integrate this with respect to y squared x minus z y plus c2. And then again, you differentiate. Then the last one is the, then the last one is this one. Integrate with respect to z. Integrate del z of phi 3 is equals to the integral. This is dz is equals to the integral of 2x squared z minus y minus 2z dz. So this is going to be phi 3 is equals to what? With respect to z, x squared z squared minus y z plus z squared plus c3. Therefore, phi, which is the scalar product, is equals to phi 1 plus phi 2 plus phi 3. So then your final scalar function is going to be, we just add there, you add x squared z squared y squared x plus, you add this one again, y squared x minus zy, and then you add the last one, which is plus x squared z squared minus y z plus z squared, and then plus c. So this is how you evaluate the scalar potential. That's basically easy. So I'm going to do another video explaining part C and D, whereby part C we're looking at the complex, we're looking at Cauchy-Riemann's theorem. Just going to dive deep on that one, and then also the line integral, we're evaluating a force, the work done by a force, whereby you're going to look at the conservative force and the non-conservative force, the principles. So on another video, I'm going to be doing C and D.